Arrachaldeón, buenas tardes, good afternoon. And in the case of Felipe and maybe Leandro, good morning.
Yes.
And bon dia. We have today in our seminar series, we have Felipe. And Felipe, here, yeah. Felipe is an applied mathematician. Yeah, he works in Rio Grande do Sul in Brazil, and that's in the southernmost part of Brazil, close to Argentina and Uruguay. And he currently holds a position as postdoctoral researcher at the Federal University of Rio Grande do Sul, where his research is focused on applying artificial intelligence algorithms in physical oceanography. And prior to that, he finished his PhD at the same university, working in applications of fluid mechanics with an exchange period at the Karlsruhe Institute of Technology in Germany. And so, Felipe Minuzzi, welcome, and we are very interested to see what you have to tell us. Yeah, please, you can start.
Thank you, Sergio. Hello, everyone. It's a pleasure to be here in this webinar and talk a little bit of what I've been researching for the past 1.5 years, close to that. So I would like to thank first of all to BC3 and Professor Sergio for the invitation. And I hope everyone can enjoy this topic, these applications of artificial intelligence to ocean waves modeling, and enjoy as much as I do researching it. As Sergio already mentioned, my name is Felipe Minuzzi, and I'm a postdoctoral researcher here at the Federal University of Rio Grande do Sul. It's a public university located in Porto Alegre, which is the capital of Rio Grande do Sul. We are very close to Argentina and Uruguay, as Sergio mentioned it, so we have a lot of in common, at least with the Spanish language. Okay, so let me share my screen first of all. Okay, can you guys see it?
Yes, yes.
Yes. Perfect.
Now we see it.
Okay. Perfect. Okay, the title of my presentation here is Artificial Intelligence Applied to Ocean Waves Forecast, Deep Learning Approach to Predict Significant Wave Height. Okay, so this, this presentation is divided as follows. So first, we have just a little bit of introduction to the topic. Then we go to the artificial neural networks, which is the artificial intelligence part of it. I will talk a little bit of the theory about it, and then the specific network that I will use in my work, which is the long short-term memory network. Then we have the applications to ocean wave modeling, how to use these networks to predict ocean waves, the results that I have, and some conclusions about it. So first of all, why ocean waves, right? So better, I think, I believe that better predictions of ocean waves are essential for several industries that define its operation based on the outcome of these predictions. So almost all engineering application that happens in the ocean, from transportation to renewable energies, going across offshore platforms and alerts of severe events, extreme events, not to mention, of course, geoscience, I think benefits from an accurate description of sea states. So nowadays, we are using artificial intelligence in several fields. Almost all fields are being modeled by artificial intelligence, and mainly these algorithms of artificial intelligence that uses data ocean waves is not different than that. So ocean waves can be simulated with physical models and mathematical tools such as WaveWatch 3 and SWAN, which are two of the most used algorithms to model ocean waves. But since not very long time ago, but a short period from now, we have the increase of the amount of data that are being produced both by agencies that collect this data, both are satellites. There are a lot of sources of data for ocean waves, and also atmospheric and climate applications, right? So the idea here is, why not use this data to improve prediction of ocean waves? So artificial intelligence comes right in this point. So more precisely, machine learning. Why machine learning? Machine learning is a subfield of artificial intelligence. So artificial intelligence can be seen as the try to make a computer has the same ability of a human being. We are not very close to that, but the world is going towards that direction, right? Inside this artificial intelligence big area, we have also the machine learning, which is the computer will learn patterns from the data. So as the name suggests, you have machine learning. So the computer will learn from something that is given to him. And the deep learning is a subfield of machine learning that actually make deeper connections between data, between the input of our data to the output of our data. So we just go a little bit further in the connection, but it's also the same as it still uses the idea of using data. So we need data, we need information. It can be any kind of data. It can be like a beautiful spreadsheet with a time series, very, very well behaved, but it can be like Twitter tweets, and also text, or anything that you can collect as data. You can use this to make some kind of prediction to the future. And our goal here is to prediction something in the future. Okay, so machine learning, the machine learning algorithms are divided in three types mainly. So the supervised learning, which is the most common algorithm of machine learning, which uses labeled data to train the algorithm. I mean, you have data for that specific variable that you want to predict, and the algorithm will try to learn something from this past data to predict the future. So it has to learn from something. Okay, this is the supervised learning. We have statistical method since 70, 80 years ago that also do that, like for instance, RIMA, which is a regression model, but any kind of regression statistical model it works like that. The difference now is that we have an increase of the computational capacity of the hardware, so it can be used. Now we can implement and code these different or more sophisticated and non-linear algorithms to predict anything that we want in the future. Okay, so this is the one that we will use here, the supervised learning. We also have unsupervised learning that I will not give past data, but actually I will just give some unlabeled data, some data, like I can give a paragraph of a text, and the algorithm will have to learn something from this paragraph. So I will not give, okay, this is the variable that I want to predict, and based on that, go further. I will not have this past data. It doesn't have any kind of understanding of the past. And the third is the reinforcement learning, which the agent will learn how to behave by performing actions and drawing intuitions. And by that, he will be penalized when he, on this agent, will miss or make some wrong decision. Like for instance, this was already used for you might have heard of the computer that beats the world chess champion. Okay, so something like that, because he studied, the computer studied, well, it's not he studied because he did study a lot of moves in the chess, and then when he make a bad move, we penalize them, so he knows that he has not, he cannot do that again. We go learning like that. In our work here, we will focus on supervised learning. So we will have past data to predict the future data. So I brought some example of some of the major machine learning algorithms that are used today and where they has already been used for. So for instance, we have some linear regression and support vector machine or regression, which are very statistical methods. A lot of applications that have been used, for instance, oil spill mapping detections, satellite image processing for land use. Then you go for definitely some machine learning algorithms like decision tree, random forest, and naive Bayes, which use the Bayes theorem from statistics. We have resource management and segment properties. Then we go for the unsupervised learning, when we do some kind of classification and clustering for the data. Okay, so I have a lot of these data. This can be something, this can be, I can separate the classification of this data. So k-means was used for clustering ocean biomes, and among others, algorithms that has already been used for prediction different kind of applications. For instance, deep learning is already been applied for wave modeling, and deep learning, machine learning, and also all these kind of algorithms are being very used for, especially for climate change, applications to climate change. In the end of my talk here, I will cite some of the applications that we are having with machine learning, especially to tackle climate change. Okay, let's go for our algorithm that we will use. Okay, so we will start talking about artificial neural networks. So among machine learning algorithms, artificial neural networks are by far the most used one. They can be seen as a machine that is designed to model the way the brain performs, how the brain performs a particular task or some kind of function of interest. So we will get the idea of how brain make the synapses, and we will translate this to something that a computer can understand. So from a mathematical standpoint, they can be seen as a multiple nonlinear regression. It's very important, the word nonlinear, because that is the difference for normal statistical regression method such as a RIMA or support vector machines. And the idea is that these artificial neural networks can capture hidden complex nonlinear relationships between the input data and the output data, or the input variables and the output variables. Okay, so, well, I am an applied mathematician, so I cannot not show some formulas, but I brought here some of the structure of artificial neural network, which is basic linear combination of weights, a linear combination of weighted inputs and some kind of bias, some kind of error. So as you can see here, each of my input will be defined as a neuron, let's say that, and this input will be multiplied by the weight of that neuron. Okay, so you have your input data here, and you feed your artificial neural network with this data, and all this data will be multiplied and sum over all these weights that are defined randomly at first. Okay? So you have calculated the importance of that input, that data. Then to create your output, you have to get this combination of weights and inputs, and then apply something that we call activation function, which is this phi here. Okay, this phi is applied both by my combination of weights and inputs and the bias of this. Well, the bias is something like the error of these inputs. And by this activation function applied to this combination, I will have the output of that. How can I say it? Of that first step of inputs data. Why do I say first step? Because we will see later that we have several steps to build this kind of network. Okay, so it mimics what the brain does when you have, okay, we have connection, we have synapses, and then when one neuron makes synapses with another neuron, we have, when this happens, is something like our activation function. It's like, okay, make something out of this. You have to make some connection here. So this activation function is very important for this. Okay. The definition of weights and the biases is in the network is defined in the learning phase of the algorithm. So we will build our artificial neural network, and then we will train the algorithm with the data that we have. Okay, this process of training with the data is something that try to minimize the performance of our network. So for instance, you have a metric in the end. So if your artificial neural network produces a nice result, you calculate this by this metric. Okay, if this is good, okay, this is your output. Otherwise, if it's not good, it go back and can start the process again. Okay, so when you do this kind of several steps with the network, we will have something like this. Okay, this is an artificial neural network divided by several layers. Okay, so this is a framework on the learning algorithm of our artificial neural network, which is called the feed-forward network, that uses the idea of the gradient descent back propagations, which is exactly this kind of, okay, I'll have my input data here, and then with this input will be multiplied by some weights, and then go again for several hidden layers here in the middle to, in the end, produce some output layer. So it gets something from the input and the multiplication. You have this value activate, some of the middle neurons are activated, and for the neurons that are definitely activated, you go further in the layer. With the ones that are not important, just stay in the prior layer of the algorithm. Okay, so this kind of architecture of input layer, hidden layer, and output layer is the idea that you can feed forward, but you cannot go back. Okay, you can go from input to the output, but you cannot go back. At least this is the first idea of an artificial neural network. So you can have a lot of hidden layers. You can define this by experimentation. It does not have a defined number of it. But if you want to do these 3 layers simulation, you must have some kind of input, output, and something in the middle. Okay. These hidden layers is what is also called the black box part of the machine learning algorithm, of the artificial neural network. And we cannot see directly what is happening there. This is the phase, mainly the phase where the computer will be thinking by himself. Okay. Okay. But there is a problem with this kind of network. For instance, as I said, you can go from the input to the output, and you can just go from one point to the other and just end your calculations, or you can just circle back, go back to the input if your output is not in some desirable metric that you define. If this output is not good, you can go back to the input with some new update weights, right? And then you go start again the process. This cyclic learning of the algorithm of the artificial neural network is called actually recurrent neural network, which is this recurrent of the learning. You can go back and learn again. So this recurrent neural network, which is just a type of artificial neural network, can consider the entire history between the inputs and the desired outputs. You can just go back on and on again until you are pleased with the output. Okay. However, in its basic configuration, it's not very. It does have some limited application, this recurrent neural network. And this is mainly because an effect known as Vanish gradient problem. So as the information circles around the recurrent neural network, the influence of an input on the hidden layer and consequently on the output either decays or blow up exponentially. So this information that are circling can either, because you are activating some neurons. So if you go back, you can just make this activation smaller and smaller, or make bigger and bigger. So this is a big problem when you circle the information through the network. Okay. One way to overcome this drawback of the recurrent neural network is this long short term memory architecture of neural networks. So for LSTMs, although this idea of circling information is maintained, the summation of the weights and the inputs is replaced by what we call a memory block, which is this part here, this square here, okay, which has 4 neural network connected and interacting together. Okay, so this architecture of LSTM is built something like that. So inside our memory block, there is one or more central cells, usually one cell in the middle. The middle of is the center of your memory block. And this cell is looped into 3 multiplicative units called the input, the output, and the forget gates. Okay, so this difference of having more units controls the flow information, because you have this multiplicative input that protects the memory block from receiving some kind of data that is irrelevant. And this, for instance, this output gate protect the network from information that should not enter this block. So the LSTM is built like with several memory blocks. All memory blocks are connected together, but each memory block makes something that will define by the importance of the data that is being fed. Okay. So that is the main difference about LSTM. So this structure of LSTM allows the network to learn and to remember information for a long time period. So this is very good if you have something like 34 years of data. So the network can go back to 34 years ago and learn the patterns that you have from these 30 years of data, and then uses that to predict the future. So you can go way back. One application of the LSTMs that is not on the ocean waves modeling, but is very, very used, that we probably use it every day, is the translation and identification of the grammar in some sentence in another language, because depending on the language that you have, okay, so you have Portuguese, for instance, you have some structuration of your sentence that maybe the middle term depends on the first and the, or something different than that, like for instance, German, that you have the verb in the end of the sentence. And how do you make this have sense? You cannot translate each word because you have a meaning, you have a sense on this sentence. So LSTM can be used to get or try to understand all the context of this sentence and more. Can go back to a full test and understand for instance, a full paragraph, if can understand something like what's the main topic of that paragraph, something if is some citation of or something that has some sense, I mean not sense, but I mean something like an emotion, the LSTM can see, okay, this is good, this is bad, and a lot of research is doing this kind of application of, well, artificial neural networks. Okay, perfect. So let's go for what we've been doing in the ocean waves modeling. Okay, so we will present here, I will present here a framework using this long short-term memory network to forecast significant ocean wave heights. Okay, this is our goal here, this variable here. Significant wave height is basically the height of waves in the ocean. You can think something like that. Okay, we will use two kind of data. Okay, so first of all, we will use the ERA 5 reanalysis data obtained from the Copernicus Climate Data Storage implemented by the ECMWF. This reanalysis data, let's say that is the best prediction that I have for that variable at that time. So they gather satellite data, also some real data after the time has passed, and also simulations, and gather all this together to make the best result, best value for the variable that we want for that specific period. Okay. We will also use real buoy measurements. For our work here, we'll have 7 buoy locations in the coast of Brazil. They are located from the north to the south. Let me show here. We have this map here. So this is the coast of Brazil, most of the coast of Brazil. I have this southmost buoy here, which is close to where I am right now, but we have locations in every kind of different depth of our buoy. For instance, we have different value of how depth this buoy is in the coast of Brazil. Okay, perfect. So this is the 7 buoy location, and we will make this prediction for what we call the lead times. Okay, so the lead time is how much time will I separate my training from getting data and getting the prediction. For instance, if I want to make some prediction 24 hours from now, okay, which is very interesting because, well, I want to know how is the ocean, the state of the ocean 24 hours from now, right? So I only have information till most of information that I will have is now, until now. So I have a period of 24 hours that I don't have any information about the sea, about the ocean, nothing about any kind of variable that makes some kind of influence on the significant wave height. And I want to make this prediction. So I will call this 24 hours period as lead time. And I will make some prediction of 4 lead times, which is 6 hours, 12 hours, let me go back, 6, 12, 18 hours, and 24 hours. So in the 6 hours lead time, I will use all the data that I have 6 hours prior to the desired hour of prediction. Okay. The metric of evaluation of my results will be the mean absolute percentage error, which is basically a mean, an average of the absolute error along the whole period of prediction. My training data set, so for the ERA 5 data set, we have the data since 1979. So I will get, first of all, I will get data from 1979 until 2018 to find that for different lead times, so for 6 or 12 or 18 or 24, the amount of data that I need for a better prediction is different. So we make different training start date. For instance, for lead number 6, I will start my training phase of the algorithm from 2003. For lead 12, I will start my training in 2002. For lead 18, 2005, and for lead 24, which, as I said earlier, I will have a gap of 24 hours to predict in the future. I will get data from 1987, so very long time ago. So I can have a nice, so I can have the better prediction, a better accuracy. So this starting dates for training was decided basically by the best metric that we have here for each of the lead time. So if we check our metric, so these graphs show, these 4 graphs show our lead times, 6, 12, 18, and 24. Okay, so for each lead time, I will check how long back I can use my start of the training, the start of my training phase, and calculate the metric here, the MAPE. So if you can see, we will have some very problems, or our metric will be very worse as I achieve to very close to the prediction period that one. For instance, this is I go from 1979 until 1 month prior to the prediction month that I want to predict. Okay, so as you can see here, if I use a lot of data, okay, I will have some good accuracies. But if I come close less than a year from this period of prediction, so data from 2017 forward, I will start to have, I start to lose accuracy. For this lead time 6, it's not a very bad accuracy, but if you go for lead time 18 and 14, we go for half of the error, basically. So we miss our prediction by half. Okay? So this was something that we need to decide, okay, I need to start my training phase from here. Okay. As I said, the starting date for the training set is different for each of the lead time. Also, the end of the database depends on the lead time because it's different. The start phase, so it will be different the end of the training. And we use different strategy for the prediction. First, we use only historical series of significant wave height in that buoy location. So I use only the historical time series of the variable, the height, to predict the future. I see in another strategy, I investigate the influence of other variables in the results based both on physical aspects or some kind of correlation analysis. For instance, I know that winds and peak period I know physically that these variables can make some influence on the significant wave height. So I will try to use these variables to improve my predictions. And also prediction using only those variables that is not the significant wave height. So these physical variables that make some sense, that we know that physically has some strong relation with the significant wave height, but I will take out the significant wave height of my simulation and use only these other variables. Okay, like these other variables are the input of my model, and the significant wave height is the target of my model. Okay. some characteristics of our network. So we will make some cross-validation scheme, which divide the training phase in 80% for training and 20% for making sure that this training is okay. We use some library in Python called Tensorflow, which is very used for artificial intelligence, especially machine learning algorithms. It's constructed by people from Google. The model is compiled using the mean absolute error as loss function. So this loss function is that function that you have to minimize, so your network produce a nice results. And our LSTM network has 3 layers, 3 hidden layers. So we have 5 layers, 1 input, 3 hidden layers, and the output layers. One with 64, one of the hidden layers with 64, the other with 48, and the last hidden layer with 32 neurons. That was decided basic on try and error to see if we change how much neurons we have. Some kind of some kind of search for the best parameters to use in this network. Okay. And for the methodology that is being different, so this is the difference that we have in our work. This is the novelty that we have in our work. We consider this lead time for every step of the prediction that we make. So for the first step of prediction, we have our training data set. We separate the end of the training by 6 hours until the first prediction. Then we go for the second step of prediction. So we will get one data more here, of course, in the training data set, and then we go for the second step prediction. So all predictions has a gap of 6 hours when the lead time is 6 hours, okay, from the training phase. So I make sure that my algorithm will see no data at all from this lead time period. Of course, for lead time 6 is a small period of time, but if you go for lead 18 and 24, you have like a day ahead to make the prediction. So there's a lot of information that is not given to the network to understand the patterns. Okay, some computational results here. Our simulation was performed in a CPU with a computer with 20 CPUs. The RAM memory of our computer was 128 gigabytes, and we used a graphical processing unit, GeForce, which has something like almost 2,000 CPUs inside of it. This library that I used, the TensorFlow library, has already implemented in itself the use of GPU when you have a GPU available in your computer. So nowadays you have these cloud computing strategies by the big tech companies that just give you the possibility of processing your results in the cloud. Okay, so comparing to the cloud potential, our computer is not very good, although it's the best one that we have. But with this kind of computational power, we achieved some, for each lead time, our algorithm took approximately 14 minutes for training, and each prediction step was like 10 to the minus 6 seconds. So this is way less than the normal mathematical model. So this was something that this is the one of the best things of the machine learning algorithm. You can have results in a very short amount of time. Okay, so I will show some results. Now you can see here I have the prediction period of the LSTM. Okay, so it's basically 1 month of period. This one is for buoy number 5, which is located in Porto Seguro, here in Brazil, is the north of Brazil. So you can see here the metric. You have some average error of 3% for the lead time 6, which makes sense because you are not very far away from the training that you have. So you only have 6 hours, so 6 time steps. But as I go further in my network, my results start to decrease a little bit. So for lead time 12, 18, and especially 24, so we have our prediction a little bit or very different from especially from the real data, which is the gray line, which is the buoy. Okay, so we compare our result with the era 5 results, which are the data that we use to train our network, and we also compare against the buoy, the real buoy observation, the real buoy measurements of the height at that specific time. Although we have some loss of accuracy, this is, of course, the best result that I have. This is done using only significant wave height as my input data for the network. So you can see that the patterns and the trend of the time series, it's well observed, is well represented by the Lstm network. Okay. Of course, if you go to lead time 24, the loss of accuracy is way more. This metric here is the average of the values, the average of the error. So for instance, here in the lead time 24, you can see here in this point here, in this area, that, well, our algorithm makes some very wrong prediction, but you go up, you go to a peak, while in the true value, the real observations go down. Okay, so this is the error, but in the average, we have some very good results. This is another result for a different buoy. This is buoy number 2, which is in south of Brazil, close to Rio Grande do Sul. And now this one is using only the period and the peak period of the waves and the winds as inputs for my prediction. So I give the input as these variables and show the algorithm to okay, you have to arrive in this significant wave height here. So it will train the algorithm to make this kind of relation. We lose some accuracy, which makes sense because we do not have the value of the significant wave height to inform to the algorithm, to the training phase. But nevertheless, we kind of have some very well behaved prediction. We can see here that it's kind of that our prediction, as the lead time goes up, the prediction will go smoothing to the average of the period of prediction. And this is some behavior that happens with LSTM's network. Okay, so when it becomes very difficult to predict or to improve your results, the network will, okay, I will just go for the average of the values because I think this is the best place that I will be. So as you can see in the results for the lead time 24, this black line here is kind of the average of the value along the prediction period. So this is one of the drawbacks of the LSTM. Nevertheless, we can have some very nice results, especially for the values of lower lead times, for instance, 6 and 12. Okay. I gather here all the results for all the buoy. I know that's not very nice to see tables in presentations, but I want to show that the worst error that we have is for lead time 24 in the buoy location number 1, which is very close to Rio Grande do Sul, the Rio Grande buoy. And for the 24 lead time, you have an error, our metric of 24.15%. So this is still quite good when you think of predictions. It's still very interesting. But the main part here, or the main outcome of our simulation, is when we compare our results that we use it, our predictions, using now just buoy measure data. So we will not use anymore the Era 5 data to train our network, but we use the real buoy prediction, real buoy measurements. Only the significant wave height will be considered in these experiments. So it will act both as the input and the output of my network. I did this simulation for only 2 buoys location because it was the one that has the best availability of data. They both have data from April 2009, so you have something like almost 10 years of data to make the predictions. But there are several missing data and outliers due to buoy maintenance or any kind of issue that happened to the buoy. Okay, the buoy number 2 has more erroneous measurements compared with buoy number 1. So to make this problem a little bit, not too much problem, we use some kind of smooth of our data by also a machine learning algorithm called the k-nearest neighbors to classify for a classification to filter this kind of outliers and this kind of error measurements. So this was done prior to the training phase. And in the end, we had some removal of 1.6 data from the time series of the observation for buoy number 1 and 14% for buoy number 2. So there's, for the buoy number 2 is a lot of data that we took it out from the time series. Okay. So now we can see this is the interesting part of the results, because we compared our results that were predicted with the buoy measurement, with the buoy, of course, and also with the Era 5, which is the best result that you have for that variable in that time. And we can see that we have some very, very good results. And also for our metric, for the average of the error, we have a metric that's smaller than the comparison between the Era 5 and the buoy measurement. So for this lead time 6, for instance, we have in the average a best result than the Era 5 data. Okay, it's not very much, but still is a better prediction. Okay, and also Era 5 does not uses this kind of lead time. So the prediction that you are seeing here, or the results that you are seeing here in the gray line, it's not done with any kind of gap between past data. So it's the best data that you have for that specific step. And also, as usual, as our lead time goes up, our metric goes worst. So this average goes way better. The metric for the Era 5 here is not different because you don't have this difference of lead time. So it's also the gray lines and the red lines here are all the same in the graphic, but the gray line, which is our predictions, are different for each one of the predictions. And again, you can see that the Lstm, the gray line, goes towards some kind of average in the lead time 24. Okay. Nevertheless, is a very good result, interesting result. I have this result for buoy number 2 here, which is also the same kind of behavior. You can see here that the Lstm could not achieve this peak that happens in this gray line. I mean, it overestimated this peak here for lead time 6, and maintain this peak for all lead times, although it could not reach this peak as the lead time go further. Here you can see that this red line, this black line goes to the average as the normal behavior when the LSTM has some problem with trying to define the patterns of the network. Okay. Okay, some conclusions that we have from our works. So we show that we can reach almost 95% for lead time number 6 in the accuracy of 95%. That means that an average metric of less than 5% for the shorter lead time, for 6 lead time. Well, for larger lead times, the accuracy naturally decreases since the gap from the training phase and the prediction is bigger. The computational time was largely decreased compared to physical models, to mathematical models that can be run for hours or even days. And one of the great things that we have here is the possibility to use the available and reliable database for predictions. So for instance, when we use it only the boy, this was, we have a slightly better result than the reanalysis itself. So we believe that we have a nice algorithm for predictions here. Okay, so I just want to show, prior to some applications, let me show you some figure, because I think it's good to show an example where something does not go quite well. So this is a result for boy number 3. We have some good results for lead time number 6. We have some average good results for lead time number 12, but check here if you can see in the lead time number 12, to this period of prediction, our prediction, okay, our black prediction line tried some kind of peak. And as you can see, you have some very well-behaved pattern of the gray line here, which is the boy observation. So why does our algorithm did such kind of peak? And that's the problem to this black boxes algorithm, such as artificial neural network. You cannot, or it's very difficult to go back and try to understand the real reason for this odd behavior. So artificial neural network, and LSTM is a kind of artificial neural networks. It's something that we cannot fully understand. Okay, so you don't know what happens or how the computer will make this kind of understanding of the data in the training phase to give that result. In fact, I can even try to run my code again, or maybe change one or two parameters, the size of the network, or maybe the quantity of neurons, and then the problem will go out because it's very random and we do not fully understand. Okay, and to overcome this kind of issue with the machine learning models, with the artificial neural networks model, there's a methodology called the physical informed machine learning, which, as the name says, try to use some kind of physical information through the power of using the past data. In fact, there's a very recent paper that was published in Nature about it. I can share with you guys later. And this kind of analysis uses a lot of physical laws and the relations that you have from the variables, such as ocean waves modeling. And this training, this learning of physical informed learning will integrate both data and the mathematical models, and will not only just replace the mathematical models, such as we did here, and implement them together, the neural network and the physical model together in some kind of regression network that uses the information from the laws of physics. And it's something that is designed to overcome this problem of you do not know where your algorithm is going wrong. For instance, why this peak is being achieved? I cannot say for sure. Okay, I cannot go back and check, okay, this is the problem, this is this phase of the learning. I cannot say anything about that. Okay. And just to finish, guys, I want to show here a little bit of how machine learning is being used for tackle climate change. So you have some very interesting article that was done for several research of machine learning researchers, which the title is Tackling Climate Change with Machine Learning. I can also share with you guys later. And for instance, you have new and cheaper satellites that are creating petabytes of observation data, or petabytes of simulations for climate data. So why not use this, for instance, for climate forecasts that usually are computationally very expensive. And with machine learning algorithms, you can just go and train our model with this past data and maybe use some kind of physical information on it so we can fully understand what happened, and trying to, in applications, for instance, for clouds, sea level rise, ice sheets, forecasting extreme events. There's some works that uses let's say screenshots of the state of the atmosphere, and uses historical information of this screenshot of the world, and try to understand when will be some kind of extreme event, some catastrophic event or something like that. Storm tracking, also contributions can include development of clean energy technologies. You can improve the forecast of demand of clean energy, so make your how do I say it, your transportation of energy more optimized. Okay, of course, the electrical vehicles, which are more efficient than combustion engines, but you can use machine learning and artificial intelligence to improve the routes and make them run smoother and better through the streets. Also, some very interesting thing is there are aerodynamic efficiency improvements that need turbulence modeling. That is the biggest problem that you have in fluid mechanics, for instance. So mathematical models for it are not fully understood. So even the mathematical models are not fully understood for turbulence. And simulation of this, although is done nowadays, is very difficult. So you can, and you have a lot of data on this kind of simulation. So why not use it with machine learning to make some kind of surrogate model for a better car, a better wing for the airplanes, or a lot of other examples. So I try to bring a little bit of how machine learning is being used on climate change. Of course, the research on machine learning is growing very fast in the past couple of years. So there's a lot of application, not only in climate change, ocean modeling, but also in medicine, social science, economics, all kind of fields of interest of the science. Okay, it's a very interesting article, this Tackling Climate Change, to show how you can use it, or what can be used to tackle climate change with machine learning. Okay, guys. So sorry if I overcome my time. Thank you very much for everybody for listening. I'm open to any kind of question. If anyone wants to contact me or send me an email, you can just find me at this email here. Thank you.
Thank you, Felipe. Yeah, thank you very much. And as was written in the chat, if you have a question, please, you can write it in the chat. And let's wait a bit to see if something comes. And while the attendees are writing their questions. I will just start with something here, which is, well, when you showed these cases in which the simulation goes crazy and there is a peak and so on, an extreme thing. So at least you say that, okay, you cannot predict it, but at least you can estimate the frequency with which this thing may occur, or a probability that it may occur, just that you can have a measure of uncertainty about that event is real or is a blimp in the simulation?
In the simulation as it is, we cannot. I mean, you cannot have the probability of that, okay, I will have this peak here. Okay. What we can do is something like an ensemble prediction. So you will make this several 20, 30 simulations with the same kind of, well, changing a little bit of the parameters of your model. And with that, you can have like some average of this 20 simulation. And then, okay, in one simulation you have the peak, but the other simulation you don't have. And in your final result will try to find something in the average of all these kind of results.
And have you tried to do that? Because you mentioned 20 simulations. I was expecting something like hundreds of simulations to 1,000, but not. You can you see it in 20 simulations. You see it several times.
Yes, you can do. Is something that I'm working now. Is like the second topic of my research is working with this kind of ensemble simulation. So try to figure out some strategy that make these several different simulations and get the best result out of this 20 or 30. And it can go to 120, 200, because as you see, the simulation cost is not very big, and both in time, computational time, and in memory. So this is something that I'm studying to get this better result and try to not have this kind of peak and have these odd behaviors in the prediction. Actually, this is done in the mathematical models. So the ensemble predictions with mathematical models, you can just change some parameters because you have some chaotic, chaotic system trying to predict on the ocean waves. So it's something similar to that with neural networks.
Okay, good. Let me see. So what we have here? So we have Massimiliano just said thank you. He found your lecture very interesting, but I've got no questions so far. So either everything was very clear or they didn't get it.
Yes.
Then I will try again, then with another one. If we go back in the results, the other results, I confess that I had some difficulties to distinguish the gray and the black curves. So it would be nice or easier if they were yellow, one of them yellow or orange.
Especially this one, I believe, right?
Yeah. But so, I see that, well, at least the red we can distinguish very well. What I notice is that the red, and in comparison to one of them, which I don't know if it's the gray or the black, but sometimes it reproduces well the shape, but sometimes it lags and sometimes it leads the shape. So the buoy data sometimes lags or leads the shape of the black curve, which is it's the less smooth. So the less smooth must be prediction. So and is there a physical explanation that the buoy historical data sometimes reproduces well, but sometimes it's behind, sometimes it's ahead of the prediction?
This is something that bothered me a lot, because first in the beginning I was having some kind of, when I increased the lead time, I was having just some kind of displacement of the result a little bit further. So I was investigating why that happens. For instance, for buoy, when I use buoy observations as the training, the problem is that I have a lot of bad data with the buoy. Okay, so I cannot trust entirely the buoy measurements. And since we have, for instance, you have the hourly time series for the buoy in that location, of course, in the location. So, for instance, for 5 o'clock, you have some nice measurement, but then for 6, you have some very, like you have 1 meter of wave high, and then go for 10 meters. So you go, no, it cannot happen this in 1 hour. So, and then you have to smooth this kind of behavior. And then one of the things that we done was to apply some classification algorithm, so can get all the data, all the steps of the buoy, of the historical series of the buoy, and see, okay, this is too much, or this is too low, this does make no sense at all, and take it out, and this makes our step not be hourly in the training phase. So you have gaps in the hourly, so it's not like very well behaved in this hourly time series, and this affect our results in the end. So because our results will be hourly, so this can be the explanation for this training.
Okay, good. Thanks. Let me see. Then no question, and then I just finish with the question: what are your plans for this kind of work? What are you planning for the next steps to connect it or offer it to stakeholders, or connect it with other kinds of simulations? You mentioned maybe to relate it with a physical model.
Yes. I have some goals that I want to do next. That for instance, okay, I have results for buoy locations. I want to make some predictions for the whole globe, or at least a region. And then you have relations, geophysical relations, like this position here makes some very high influence in the other positions. So we have to see how we can track all that. So make some kind of prediction for a full region, that I will have to use another kind of neural network, which is called the convolutional neural network, that was built exactly for this kind of problem. We have two-dimensional data. So you have influence of the positions. So let's see, get the whole globe, right? You have differences in the ocean waves that are influenced by all the parameters. I want to work a little bit more on this ensemble idea that we mentioned earlier. So how can we improve the predictions when you use several simulations together? We can use different neural networks and try to find the best one, an average of all the networks. You can use the same network and change parameters so you can have better results. Or you can use this ensemble forecast, the ensemble data itself from the agencies, from ECMWF or on any other agency, and use this data to make some kind of difference, because nowadays this ensemble uses mainly the average of the other ensemble, so uses machine learning to have a better average, or something that replaces this kind of average. What else? I think there's a lot of things, but one of the things that bother me as a mathematician, and also something that someone that likes to understand everything that I did, is that I cannot understand fully what happens in the neural network. So I think this physical informed machine learning is something that we can just go true, because we have something that is well established, which is the machine learning models. We have some physical laws that are way well established, so why not use them together and try to make one better with the other, with the mathematical models, and not just this kind of surrogate that replace it and have this drawback of not understanding everything that happened in the simulation.
But are you sure that combining them we will have the best of both and not the worst of both, and we'll make them worse?
Yeah, we have to try to create an algorithm that gets the better of both.
Yeah.
Yes, definitely. But it's
okay.
Something that we have to worry about.
Yeah. 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 Thank you very much, Felipe. Thank you all who attended this seminar and this webinar, and have a nice evening. And for those in Brazil, have a nice afternoon. And you have the contact of Felipe. Feel free to contact him or contact us. And we are also in constant contact with Felipe if you want to discuss anything else. Thank you very much all. Esquericasco, and muchas gracias y obrigado. Y agur. Ciao.
Ciao. Thanks, guy. Thank you.
Thank you.
Bye-bye.
Bye. Oh, Felipe.
Okay, yes, Antonio.
And now comes one.
Yes.
From Antonio. Antonio is there. Oh, okay. Yes. Antonio is there. So you can answer. So the question, I will read it for you, but you have it. Have you thought about using more interpretable DL is what is the
yes, I never actually, well, I've read a lot about interpretable deep learning algorithms.
Deep learning,
deep learning, yes. But these temporal fusion transformers, I have to say that I haven't heard of it. But yes, it's exactly this kind of technique that I'm looking for to work on, because this interpretable, or this thing that we can have some information about the training, is perfect for this kind of natural science modeling that we are having nowadays. So I will get this archive file and definitely take a look. Thank you, Antonio.
Yeah, it's a bombastic name. Yeah, I wonder how long they thought about it to have this name, temporal fusion transformer.
Yes.
Wow, that's really cool name. Yeah. Okay, I didn't hear about
time series. Perfect. Yes. Thank you. Thanks a lot, Antonio.
Yeah, thank you, Antonio, for the question. And then now we close. Thank you very much. Thank you, Antonio, Nicolas, Alexander. And have a nice evening. Thank you, Felipe.
Okay, guys.
Bye-bye.
Have a nice evening. Bye-bye. Thank you.